Hi, welcome back. In part 1, we looked at solving limits graphically. If we can have a graph and we know functions coming in from the left and the right, we can actually kind of determine what the function is approaching. Now, for some functions, let's say we're not given a graph, in some functions it is actually easier to graph a function to determine their limits rather than solving them algebraically. This is especially true when we look at step functions. So we're going to take a look at some step functions. Now the first one we're going to look at is that weird absolute value function. You may not remember what it looks like. That was just absolute value of x over x. And I know you all know what it's going to look like. Now this is an interesting function because if you notice here, we have a domain restriction, right? X can't be 0. So that's going to cause some problems for us. So what we do is we want to find out, well, what's happening as this function approaches 0. So we want to find out what happens as x approaches 0. And to find that out, sometimes it's easier to graph it. Now the first thing we can do is we can write this as a piecewise function, and if we did that, it's pretty easy. The first one is just going to be, if we think about this absolute value of x over x, right? If we have the absolute value of x over x, that just really becomes plus or minus x over x, or plus or minus 1. So if you notice, we have two functions. We have positive 1 and negative 1. And we generally say it's going to be 1 for x is greater than 0, and negative 1 for x is less than 0. So, and I can use this. So as I approach 0, on the left, on the right side, notice our value is getting closer to 1. But on the left side, our approach is negative 1. So I know already at 0, the limit doesn't actually exist because one's approaching from the positive, one's approaching from the negative. Now, this one's not so bad, but we can obviously come up with some really complex functions like this that may make it a little bit harder to write them as a piecewise function. So another way we can do it is just to graph them. So, and here we have it. Hopefully we recall from pre-cal what this graph looks like. And again, we know if x is greater than 0, it's positive 1. Less than 0, it's negative 1. So here we have our function. Now again, for this one, we want to evaluate the limit as x approaches 0 from the right. There's our right side. Now again, I want to find out what this limit is equal to right here. So if I were to do that, I would say the limit as x approaches 0 from the right of our function, the absolute value of x over x is, so I'm going to graph it. And again, I can get my graph from up here, and I already graphed it right over here. Remember, anything left greater than 0, the value is 1. Now kind of remember, these are both open circles right there. So anything to the right is positive 1, anything to the left is negative 1. So if I'm coming in from the right side, we know that this will equal 1. And there's our answer. If it goes from the left, if we want to show that, if we want to take the limit as x approaches 0 from the left, that's going to become negative 1. Now the next question says, is the function continuous at x equals 0? And you might recall from the first video that of course this answer is no, and the reason why, the value does not equal, the limit. Now there's actually a more specific reason. Here we can't even do this, so it's okay to say the value does not equal the limit. I mean, we'll talk more specifically about this, but really what we should say is that the limit doesn't even exist, right? So we just really say that the limit does not exist there. If you can't have a limit, you can't have continuity anyways. And again, we're going to talk about that later on. So let's try a couple more. Now there's a couple ways we can do this. One, if you notice here, we have this limit right here. And if you notice, if we ignore the 2, we have our new rule up here. We have our absolute value over x. And I can write this as two separate limits. Remember that 2 is just a constant, so I can write that 2 outside. Oops, that guy went away for some reason. So if I write that 2, we get the limit as x approaches 1 from the left of the absolute value of x minus 1 over x minus 1. And if I were to graph this, my one domain restriction is at x equals 1. Really quick and easy, it's going to be 1 for anything to the right, and it's going to be negative 1 for anything to the left. So as we approach from the left, we know that this is going to be approaching negative 1. We're on the left side. So this has become 2 times negative 1, and we get negative 2. Now, of course, you don't have to necessarily do it this way. Some of you guys might be so good that you're going to memorize this, okay? You're going to memorize this. This is either plus or minus 1. It has to be, because notice I'm taking the same on top and the same on bottom, and I'm and there just becomes 1. The absolute value makes my plus or minus right there. And in this case, because I'm going from the left, it's going to be my negative 1. And it's okay to kind of jump to that real quick. We would expect you to be able to do that. All right, we see the same thing similar to on number 2 right here. And again, notice there's your weird absolute value function. But you got to be careful. In this case, we have this x squared here. Over here, we can just factor out that constant. But over here, we have that x squared right there. So when I rewrite this, now, when you rewrite this, notice I'm going to write that limit again. You always want to rewrite that limit. X squared times the limit as x approaches negative 2 from the right of x plus 2 over x plus 2. Now in this case right here, remember the AP wants you to rewrite these, okay? But if you forget to rewrite these for now, we're going to be okay with that. We just want to get better by the end of the year. Now here I can just substitute in. This is just a parabola. And what's the value of a parabola? As we approach negative 2, it's just 4. So this is just going to become 4 right there. Pretty easy to do. Over here, remember, this is just my plus or minus 1. I'm approaching from the right, so it's going to become a positive 1. And we just get 4 right there. Pretty easy to do. All right, number 3 is kind of a tricky one right here. You want to be really careful. Notice we want the actual limit. We don't have to do much for this one. Of course, if I rewrite it, the limit as x approaches 4 of the absolute value of x minus 4 over x minus 4. This is the one we want to be careful. If we look at it graphically, my unknown is at 4. There's my we call it a discontinuity. We'll talk about that later on. We're either going to be positive 1 or negative 1. But notice there is no plus or minus right up here, which means that we want to come in from both sides. This one needs both sides. And if you notice from the left and the right, we're not approaching the same value. So because we're not approaching the same value on both sides, this is a DNE. Right there. Just does not exist. Very easy to do. All right, now the other step function we tend to see is the greatest integer function. You call it, it's a kind of a GIF for us, or GIF, I don't know, however you guys want to talk about those nowadays. Now this one we may be able to solve by graphing, and if you remember the greatest integer function, it looks like this. Remember, these are all open circles there, right there, open, 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 right? They're all open circles here. And whoops, it did not print very well, so I apologize for that. There we go. That's our greatest integer function. So for some reason, it's not showing up well here, but I think it does show up on your notes. I don't know what's going on. So I will kind of fix that real quick here. So if you give me 1 minute. There we go. I had to kind of fix them all down here. For some reason, it didn't copy right. So this is our greatest integer function. It's sometimes called a floor function. Now, one thing that we should really notice is that between any integer, we always go back to the smallest integer value. So if we go between integers, the value falls to the smallest integer. Into the smallest, there we go, integer. Why do we call it the floor? So anything between 1 and 2, like 1.5, falls to the value of 1. We don't go to the largest. We go to the, in other words, we go to the greatest integer that we've already reached. So let's say we want to find the limit of the greatest integer function as x approaches -1 and from the left. So let's see here. So we're going to be at -1. Here's -1, but we want to be to the left of -1. Well, anywhere to the left of -1, now we can't go to -2, that goes too far. So if we go to -1, if we plug it in here, oh, there it is. Well, what value are we on? -2. So we go to the greatest integer that we always pass. Remember, our answer is between our integers are going to be between 1.5, -1.5 is between -2 and -1. Well, the smallest integer there is a -2 right here. So there we go. So this just becomes -2. And whoop, this should be a plus sign right there. So what if we go from the right side of -1? Well, anything between -1 and 0 falls to -1. And there's our answer. Now, we could look at these graphically, but some of you guys may remember, like example number 2 here, sometimes these are not easy to do, or easy to graph, or it just takes too much time. So here's what I'm going to tell you to do. What you're going to do is the easy way is to just pick a number close to the limit. And let me show you what I mean by that. Let's take a look at number 1 right here. We have the greatest integer function here of x minus 3, and we're approaching -2 from the right side. So what I'm going to do here is I'm going to say, well, give me a number close to -2, but on the right side of it. So I can let x equal, on the right side, it would be something like -1.9. And I can plug that in. I can just substitute that in. This is about the same as if I just plug in -1.9 minus 3, and this becomes -4.9. So what's the greatest integer of -4.9? Well, -4.9 is between -5 and, of course, -4. Well, what are we between here right now? Well, -4.9 is between there. So I'm going to go to the smallest value, which of course is for us -5. Remember, -5 is actually smaller than -4. What about something like right here? I want, as x approaches 1 from the left side. Well, I'm going to let x here. Well, what's to the left of 1? Something like 0.9. Again, I can't go to 0 because 0 is too far. And I can just simplify this. This becomes 3 times 0.9. So that becomes 2.7 plus 1, which is the greatest integer of 3.7. And to do this real quickly, this just becomes, well, remember, 3.7 is between 3 and like I said, since we're between 3 and 4, well, what's the smaller value? Obviously 3. So this is going to become 3 right there. Now let's go and try a couple more here. Ready? Let's see here. Let's see. If I plug in something 3 to the left, I can let x equal 2.9. And if I take 3 times 2.9 plus 2.9, and I'm going to cheat here. I'm going to use a calculator. Okay. So if I go to home screen, homies. If I go 3 times 2.9 plus 2.9, it gives me 11.6. So 11.6 is, of course, between 11 and 12. The smallest number is 11. So we should get 11 for our answer right there. So this function, as x is approaching 3 from the left, is approaching 11. And this is a lot easier than graphing these. These weren't very easy to graph, if you remember from last year. All right, here's a trick question right here. Okay, we're approaching -4. Oh, man. But notice, we're not looking left and right. This is both sides. So this one should not take us very long. Remember, at an integer, it's not continuous, or it's not. There's no limit. Notice, there are no limits at the integers. The limit does not exist at integer values. So since I'm only looking at an integer value, I can only do a right or left side. So since I'm looking for both sides, this is just going to be a D and E. And again, this is going to be D and E because the limit does not exist. Remember, my step functions, they look like this, right? My left and the right aren't equal, so the limit cannot exist. I can have a left limit and I can have a right limit independently, but not together here. All right, I hope you enjoyed the video. Smash that like button.